Okay, so this is part 1 of lesson 4.6. In this part of the lesson, we're going to explore how transformations change the domain, range, y-intercept, and asymptote of a exponential function. And at this stage, I would not expect you to be able to come up with this. If I was to ask you to do this at this stage, before this lesson, I would ask you to graph these in Desmos and look for these properties from the graph. And going forward, after the discussion about how these transformations change the values, we can come up with them by actually sketching a graph. And we're going to do that in the second part of the lesson. In this lesson, we're also going to look at how we can use exponent rules to simplify exponential equations so that when we graph them, we can actually do a little bit less work. We can take some of the transformations and just change the base and graph a different base, which is kind of neat. So we're going to look at that as well. Let's start with the transformations and how they change the domain, range, y-intercept, and asymptote. So the first function here, we have f of x is 2 to the exponent x. So this is our base growth function with a base of 2. No transformations have been applied, as that's one of our parent functions, and these were the properties that we explored in the last lesson. I had a asymptote of, that's not right, y equals 0, because it's a horizontal asymptote. It had a y-intercept of 1. It had a range, y greater than 0, and the domain was x belongs to real. And in fact, every transformation we're going to do to all of these graphs from here to here, none of them are actually going to change the domain, which is kind of nice. The domain will always be x belongs to real. So we can begin by filling that out, because no matter what exponential equation we have with a base of 2, we can put any x value into the input or into the x, the function, and get a y value. So there's no restriction on the range no matter how we transform the graph. So let's look at our first transformation. If we have a 3 in front of our function multiplying, that's an a. In this case, it's a equals 3. And the transformation for a equals 3 would be a vertical stretch. And by a factor of, I'm just going to say factor 3. So what would this do to the graph? Well, it would stretch the graph. That wouldn't really change the range, though. It's going to change the fact that it approaches the asymptote, and it's not going to change the asymptote either. So these actually stay the same. What it does change is the y-intercept, and we can figure that out by just plugging 0 in. If we plug 1, we've got 2 to the exponent of 0, which is 1. 1 times 3 is 3. We get a different y-intercept, 0, 3. So changing the a value changed the y-intercept. Everything else stayed the same. What if we make the a value a number less than 1, like 0.5? Well, in this case, it would be a vertical compression. And the factor would be, well, since we have 0.5, we wouldn't write 0.5. We'd do 1 over 0.5, which is 2. So our value would be compressed by a factor of 2. And again, the range wouldn't change. And we could see that by graphing on Desmos. The asymptote doesn't change either. What does change again, though, is the y-intercept. If we plug 0 in, we get 2 to the exponent of 0, which is 1. 1 times 0.5 is 0.5. So again, even if we change a to 0.5, the only thing we're changing is the y-intercept. What happens if we make a negative? So in this case, we've got -1 in the a spot. What would that change? Well, we would anticipate that it's going to change the y-intercept, just like it has in the previous 3 examples, because this time we have a vertical reflection. Or we could say reflection over the x-axis. If we think about what our graph looks like reflected over the x-axis, really quickly up here, I'm just going to draw a sketch. We remember what 2 to the x looks like from yesterday's lesson. It starts low and goes like this. So what would happen if we took that graph and flipped it vertically? Well, our graph would just end up down here. And what that would change is actually the range. The range no longer would be greater than 0, y is greater than 0. If we're down here, it would actually be y is less than 0. So this time, if we do a reflection, it changes the sign in the range. I should have used a different color, I just realized. If you're following along at home and used the same color, I'm really sorry, I'm gonna modify it and use a different color. If you pick a color that goes over yellow, it works out kind of nice. But a reflection, an A of -1, changes the sign of the range because it flips it. Now, also the y-intercept's changed, because if we do the math, we should get -1 now, and the asymptote didn't change. So a negative value, again, still continued to change the y-intercept, but the fact that it was negative changed the range. Now, what if we add 1 to the end of the function? Well, that would be a c value. That would be a c of 1. What's that? That's a vertical shift up 1. And if we took this graph and moved it all up 1, what it would change is actually a lot of things. It would change the asymptote, because it would now be 1. The y-intercept was again changed, because instead of being at 0, 1, if we shifted up 1, it would be at 0, 2. And the range would change, because if our asymptote is now y equals 1, our graph's approaching y equals 1. Now y has to be greater than 1. So the c value actually has a pretty significant impact. Shifting the graph up or down changes the restriction on the range because it changes the asymptote. And also the y-intercept changes. Boy, basically every time we do a transformation, the y-intercept changes. All right, the only one we haven't talked about is d. That's if we add or subtract from the x value. In this case, we've got a d of -1. And the question is, what's that change? Let's give it its own color. This would be a horizontal shift, or you could just say shift left 1. Well, what would that do? Well, if we look at our graph here and we shift it to the left 1, is that going to change the domain? No. Is that going to change the range? No, because we just shifted left. We're still approaching the asymptote. That doesn't change the asymptote either, because if we shift left, that line still is horizontal right on the x-axis. So it doesn't change the range. It's back to the parent range. It didn't change the asymptote. The only thing it changed was the y-intercept, but everything seems to change the y-intercept. If we put 0 in, we get 0 plus 1. 2 to the exponent 1 is 2. We get 0, 2. So it seems like no matter what we change in terms of transformations, we impact the y-intercept, which is notable. But the only other transformations that we can do that change any properties are if we do a vertical reflection. We've changed the range. Horizontal reflection, I know we skipped it. It doesn't change the range either. Just a vertical reflection changes the sign in the range, and any shift up or down will change the asymptote, which therefore changes the restriction on the range. So the big ones to consider when looking at changes of properties are vertical reflections and vertical shifts. Those are the big ones. So watch for vertical reflections and vertical shifts when you're asked to find properties of exponential functions. All right. So sometimes horizontal stretches, compressions, and reflections can be applied by simplifying the power based on exponent rules and changing the base function. It's similar to simplifying the k value in a quadratic function. And you might have noticed that when you learned quadratics and all the transformations, there was only a, h, and k. There was no horizontal transformation. Like you never saw something like this with a, what we call it a k value, with a k value. The k value we knew in quadratics was the h and k of the vertex. but no horizontal stretch or compression. And that's because you can simplify this. You can square the 2 and square the x minus 1. If you square the 2, you get 4. And if you square the x minus 1, you get x minus 1 squared, which in effect takes that k value, squares it, brings it outside the bracket, and makes it an a value. And that's why you never learned about horizontal stretches or compressions when you learned quadratics, because you can always simplify a horizontal stretch or compression into a vertical stretch or compression. And that was a neat property of quadratic functions. And there's neat properties that are similar with exponential functions where you can simplify transformations and sometimes just ignore them altogether and graph a different base function. So I'm going to show you 3 examples. And if you ever notice you can use exponent rules to manipulate a question, you can get to the graph a little bit quicker. And it's an option for you. It's not a requirement. So if I give you this graph and you want to graph it as you see it, a base function of 4 to the exponent x with a horizontal reflection, 100% you should do that. Alternatively, I can show you an exponent rule that changes this. So as we see it now, if we wanted to graph this, this would be a parent y equals 4 to the exponent x with a horizontal reflection. However, due to exponent rules, we can modify this. And if we remember the negative exponent rule says flip the base and change the sign. Well, if I flip the base is 4 over 1. If I flip it, I get 1 over 4. Change the sign of the exponent to x. I now have a new parent function, 1 over 4 to the exponent x, with no transformation. So if I was graphing this function, I would graph 4 to the exponent x and apply a horizontal reflection. Or I would use the exponent rules and realize, hey, I can just flip the base, and now I'm just graphing a parent function, 1/4 to the exponent x. And we know how to graph parent functions. You take those standard x values, -2, -1, 0, 1, 2, build a table of values and plot the 5 points. And that's really easy. If I want to graph this, I have to do all that same work for the parent function 4 to the exponent x, and then do mapping notation and reflect horizontally and come up with a second table and then graph it. So this requires twice as much work as just applying the exponent rule. So you would have the option if you were asked to graph. Do you want to apply the exponent rule and change the base, or do you want to just graph the original parent function and a transformation? Up to you. Another exponent rule we can use is when we have a k value, like 2, we remember the exponent rule to say that 2 times x is what we have as our exponent. If we work backwards, when would we multiply exponents? Well, that's when we have an exponent of an exponent. So this can be rewritten like this. Knowing that if we were to multiply 2 and x, we would get 3 to the exponent 2x. We've just used the exponent rule backwards. Now, why would we do that? Well, 3 squared is a number. That's 9. So 3 to the exponent 2x is really just 9 to the exponent x. If we were graphing what you saw on paper, we would be graphing the parent, y equals 3 to the exponent x, and we would be doing a horizontal compression by 2. That's a parent function and a transformation. Alternatively, if you use your exponent rules, we're just graphing the parent function 9 to the exponent x. Both give you the exact same graph. If you Desmos 3 to the exponent 2x and 9 to the exponent x, you get the same graph. Same as the first one. If you graph 4 to the exponent negative x and 1/4 to the exponent x, you get the same graph. So the only reason I'm showing you this is to try to potentially make you more efficient at graphing. But if you want to take the long approach and just take it at face value, that's fine too. And you'll get the exact same graph. And for the most part, that's how I'm going to do most of the examples. But if you want to use exponent rules, you can get there a little bit quicker. This is a nice one too. 9 to the exponent 0.5x. It's the same exponent rule. We can break it down to 9 to the exponent 0.5 to the exponent x. 9 to the exponent 0.5, well, 0.5 is a half, and a half means square root. If we square root 9, we get 3. Graphing 3 to the exponent x is pretty easy. It's just a parent function. If we wanted to graph the original, we'd have to graph the parent, 9 to the exponent x, and a horizontal stretch by 2. So this is how we can take k values, use exponent rules to simplify. In fact, you can take horizontal shifts and simplify them as different transformations as well. But this one allows you just to change the base, which is really nice. So switching between 2 different types of transformations may not save you a lot of work, but in the purposes of k, we can generally simplify them right out and not worry about them at all. Okay, so with all of that background, let's do a transformation of a base function. Let's come up with a graph. We're not going to do any manipulation of the base. We're just going to use the base as standard. So that's our last example today. Let's give it a shot. Given the base function f of x equals 2 to the exponent x, use your knowledge of transformations to sketch the graph y equals 2 to the exponent -1/2 x plus 1 minus 2. Now, in order to do that, we need a couple things. We need a parent function table. We have a graph here, so we could pick points off the graph, or we could remember what the parent function is. I'm just going to write it up here. The parent function, don't worry, we don't need this part of the graph, is 2 to the exponent x, and we'd use our standard x values. And if we plug those into 2 to the exponent x, we get, we get 1/4, 1/2, 1, 2, and 4. And if we read those off, I think we can get all those. Let's see, -2 is 1/4, -1 is 1/2, 0 is 1, 1 is 2, 2 is 4. There's our points. We could extend, and you can actually get 3 as well. 3 is 8. That's a nice one. But we'll use these 5 points. So now what we need to do is we need to use our mapping notation on these points to come up with our new table. So I'm going to make my new table over here. In order to map, we need to know k, d, a, and c. So let's look at our function, see if we can pick those out. A would be a number in front of the base multiplying. And if we look at this, we have no number in front multiplying the base. The base is 2. So that just means that A is 1. C is any number adding or subtracting to the power. Well, here's our power. The number adding or subtracting is -2. So C is -2. We can take our A and C and we can write our mapping notation for y's now. 1 times y minus 2 would be our mapping notation. So I'm just going to write y minus 2. Now, k and d, we need to be careful. To get k, we need to make sure that k is common factored from around our x. So if you see a number and then a bracket, then x, it means it's been common factored. If you don't see that bracket, it means you need to common factor it. So we actually need to modify this equation by common factoring the -1/2. -1/2 bracket x. To common factor it from both of these terms, we need to divide both by -1/2. -1/2 x divided by -1/2 just leaves us with x. And 1 divided by -1/2 would leave us with -2. And this will allow us to get the right k. K is -1/2. And we've seen up here how we can use those, or sorry, we saw in example 2 how we could use that k value and change the base. We're not going to do that though. And then D would be 2. So we need to take our k and do 1 over k, which would flip k. So instead of -1/2, we would get -2. So we have -2x. And then we have plus 2. -2x plus 2. And If you would prefer just to write x divided by -1/2, that's fine. But if you simplify it, it maybe makes it a little bit easier. All right, now we got to do a little bit of math. -2 times -2 is 4, plus 2 is 6. -1 times -2 is 2, plus 2 is 4. And if I continue, I get 2, 0, and -2. Y minus 2, so 1/4 minus 2 would be, I'm going to use a decimal, -1.75. 1/2 minus 2 would be -1.5. I can use fractions, but decimals make it a little bit easier to graph, and these are nice decimals. 1 minus 2 is -1. 2 minus 2 is 0. And 4 minus 2 is 2. So now we have 5 new points. We can take those 5 new points and we can graph them, and then we'll have a sketch. What happens to our asymptote? Let's check back, because we also do need to graph the asymptote. So let's go back here and check. Which one changed the asymptote? Well, the asymptote was changed in this one, which was when you had a C value. So if we shift up, the asymptote shifts up as well. So let's go look. In this one, we didn't shift up, we shifted down 2. So our asymptote is going to be y equals -2. We're going to shift down 2 as well. So I'm going to put that on my graph first. That would be right here. We do asymptotes with dashed lines. And our graph is going to approach this dashed line. And over on the side, I'm just going to label it y equals -2. So I'll show you the label. Okay, and now we plot our points. 6, -1.5, or 1.75, so 6. -1, -1.5, -1.75. There's our point. 4, -1/2 would be right here. And 2, -1 would be right here. And 0, 0, well, that's the origin. And -2, 2 would be here. So as we can see, we've got our curve, which is fairly flat. And this is where we start to go up, extend a little bit, and draw an arrow. And there we have our transform function. Label it with our equation. You can use the one that you've common factored or the one that you didn't. I'll just use the one the question gave. X plus 1 minus 2. There we have it, a transformed exponential function with the base of 2. 3 properties. Y-intercept, that was 0, 0. We can read it right off the graph. Y-intercept. Domain didn't change. X belongs to real. And the range did change because we shifted down 2. So we've got y belongs to real. Y must be greater than -2. All right, there we have it. Transformed parent function, or transformed exponential function with its properties using mapping notation. Okay, that's it for part 1. I'll see you for part 2.